Today we're talking about machine translation, taking a sentence in another language and turning it into an English sentence. First, we'll begin with an introduction to what machine translation is, the components of machine translation systems, and then we'll talk specifically about word-based models of machine translation, and then very briefly at the end we'll talk about how to extend these systems beyond word-based models. For many years we didn't know how to read Egyptian hieroglyphics. And the breakthrough that allowed us to finally unlock the meaning of these words was this stone here called the Rosetta Stone that had text in both Greek and Egyptian hieroglyphics. And when we found this stone, we were able to understand, finally, Egyptian hieroglyphics. This is called a parallel text because it has the same content in two different languages. And these data are what makes machine translation possible. And fortunately for us, there are a lot of organic ways that these data are created. So for example, some governments require translations in multiple languages. So for example, the European Union, Canada, Hong Kong, many newspapers have translations of the same article into multiple languages. And if you look on the web, there are many web pages that exist in multiple languages. And these parallel texts have allowed the statistical revolution in machine translation that actually makes fairly reasonable systems. So what you do is you gather up a bunch of parallel text, you do a statistical analysis of that text, and that creates a translation model. But these translation models don't always do a good job of capturing, say, selectional preferences that we talked about last week. They don't know to prefer strong T over powerful T. To capture this sort of thing, you need good language models, and these are things that we talked about before in previous weeks, and these are learned entirely on English text. And then, together, these are combined in what's called a decoding algorithm that allows you to select over all of the many different English translations of a sentence the one that best translates the foreign phrase that you wanted to translate. And so I just want to concentrate a little bit here on terminology. We're going to represent the input to the system, and we'll call that the source language or the foreign text, and we'll represent that with an F. And for the purposes of discussion, today we're going to be talking about only translation into English, but obviously the techniques here extend to other directions, but this will make it a little bit easier to talk about it. And we'll try to create English sentences E that best represent the foreign input F. And we'll call this the target language or English. And in particular, we're going to focus on word-based translation systems. What we can do is look at a big parallel corpus and figure out all the times that you saw the German word house, H-A-U-S, how many times did that get translated into various English words? And we can count that up, and then we can create a probability. So given that your foreign word was house, what is the probability of various English words being the translation? The way that we can count these things up is we need something called alignment that tells us which German words, which foreign words align with what English words. So for example, the German sentence, das Haus ist klein, you have a one-to-one alignment to the English words, the house is small. And we're going to call this an alignment function. So it's basically a mapping from every English word to some German word. And alignments don't have to be one-to-one. You can have reordering. So klein ist das Haus is a perfectly reasonable German sentence, and you have this alignment. You can also have a one-to-many translation. So the sentence das Haus ist klein, there the final German word is translated into two distinct English words. You can also have words that drop. So das Haus ist klein may be translated as house is small, dropping the article. You can also insert words. So to accommodate this, we'll add an additional null word at the beginning of the foreign sentences. And if we have an extra word that appears in the English translation, we'll align the extra word in the English translation with the null word. So das Haus ist klein, if that gets translated as the house is just small, just aligns with the null German word. And about 20 years ago, these statistical translation techniques really began. And this happened in a fairly large research team at IBM, and they created a bunch of different statistical translation algorithms. They were uncreatively named Model 1, Model 2, Model 3, Model 4, Model 5. And despite their uncreative names, they form the foundation of all modern translation algorithms. And we're going to talk about the first translation model called Model 1 for the majority of the rest of this class before talking about the stuff that came after. What IBM Model 1 does is breaks up the translation process into smaller steps. So let's take a look at this equation. So you first have a product over all of the words in your English sentence. And each of these English words is assumed to come from some foreign word. So which foreign word did it come from? It came from the foreign word that the jth English word was aligned with. And so you look up that word in your foreign sentence based on the position of the alignment, and then you can look up the score. What is the probability of getting English word J from that foreign word based on the alignment? And this is just a probability. We represent that probability with a t. This is parameterized by an English word and a foreign word. You can just look up that probability. And then you have a normalization constant that makes this all sum to 1. And then you have the probability of all of the alignments, and the total number of the alignments possible is the length of the foreign string plus 1. So the plus 1 is there because of that null word that we added. And that's to the power of the length of the English sentence, because each foreign word can be aligned to one of the English words. And the number of words is just the length of the English sentence. So let's take a look at an example of this. So let's say that you have Das Haus ist klein, and the alignment is the one-to-one translation, the easiest one that we saw. And so here we have, there are 4 to the 3 possible alignments. So the first probability is epsilon over 4 to the 3, and then you multiply that by each of the word translation terms for the probability of the given das, the probability of Haus given Haus, the probability of is given ist, and the probability of small given klein. And so that gives you some value as 0.0028 times epsilon. Okay, so that's how we score a translation if we know the parameters t for this translation model. But how do we learn those parameters? And so it would be easy to learn those parameters if we had the alignments, but we don't have the alignments. So this is a chicken and egg problem. If we had the alignments, we could get the translation probabilities. If we had the parameters, we could get the alignments. So a common solution when you have this kind of problem in statistical machine learning is to apply the expectation maximization algorithm. And so what you do is you initialize your model parameters somehow, and then given those parameters, you compute expectations over what you think the missing data should be. In this case, it's the alignments. And given those alignments, given those missing data, you compute your model parameters given those complete data. And then you repeat those steps until you get a final answer. So in this case, what we're doing is we're trying to figure out alignments. And so we start thinking that all alignments are equally likely, and then we learn translation parameters given those alignments. After one iteration, we learn that the probability of getting the word the given the foreign word la is higher, and so that changes our idea of what the alignments should be. So we'll think that the expected number of alignments where the aligns with la is going to be higher. And given that we know that the should align with la, that will make other alignment positions more compatible. So for example, we'll prefer that fleur and flower get aligned. And then finally we'll get a converged answer where we prefer, very specifically, some words to align with other words. And this is what can happen with EM. And from those good alignments, we also get good parameter estimations, in this case, the word translation probabilities. Okay, so more concretely, the EM algorithm consists of 2 steps. First, the expectation step, where we apply the model to the data, and we get out of that the revealed hidden structure, in this case, the alignments. And given those alignments, we compute the model parameter, in this case, the word translation probabilities. And so we just take the alignments that we get out of the expectation step as truth, and given those alignments, we compute the translation probabilities. And we just repeat these steps until we get a final answer. And so there are two steps that we need to do. We need to do the expectation step. What are the probability of alignments? And then we need to do the maximization step, which is basically just counting up the number of times that words get aligned to each other. This is a very brief example. So given some initial word translation probabilities, we can compute the probability of alignments. And so over all of the possible alignments, we can figure out the probability of those alignments. And then given the probability of those alignments, we can compute up the expected counts. So we can compute up what is the probability of the alignments where the was aligned with la. And we can compute that up, summing over all alignments, to create counts for how many times the aligned with la. And then we can normalize those to create probabilities. This means that what we need to do is compute the probability of an alignment given a complete English foreign sentence pair. And if you remember what we talked about at the very beginning of the class, this is just an application of the chain rule. Model 1 tells us what is the probability of an English sentence and an alignment given a foreign string, and so we just need to compute the probability of an English string given a foreign string in order to complete that equation, and this is just a marginalization. We marginalize out over all of the alignments. So what's an alignment? An alignment is, for every position on the English sentence, we're aligned with one of the foreign words. So we sum over all of the possible alignments that we could get, and then we can compute the probability of that specific alignment and the English sentence that we observed. And so what's the probability of an English sentence and an alignment given a foreign sentence? This is just the definition of Model 1, so we plug in that. And so now we've substituted everything in, now we need to simplify it. So this is the same expression, and now what we can notice is that the probability of alignments is constant. So we can just move that to the left, outside of the sums, but then we still have these messy sums and then a product. And so we need a algebra trick in order to handle this, and what we can do is we can turn the sum over products into a product over sums, and this makes it a lot simpler. So why can we do this? We can take a look at one example of this, where we just have two words in our sentences, and this is just applying some basic algebra. So we take a bunch of sums of products, and then we can factorize them out into two products of sums. And so, combining the definition of Model 1 with the marginalized probability of the English sentence, we now can get this, and a lot of stuff cancels. So the probability of an alignment is just this, proportional to the probability of those translations given that alignment. And so now what we have to do is collect the counts. And so to collect the number of times that word E, so this isn't in bold, so notice the distinction between the non-bold and the bold stuff. So a single word E in English being translated from a single word F in the foreign language, given the English sentence E and the foreign sentence F. To compute that, we sum over all of the possible alignments, multiply the probability of that alignment given that sentence, times the number of times the English word E was aligned with the foreign word F in that alignment. And then you can apply the same trick before, and it simplifies very nicely. So the expected number of counts of translating English word E from foreign word F is just this bottom equation. So now we can put this together into a maximum likelihood probability estimate, and then we can get the probability of translating English word E from foreign word F, just summing over all of the sentences in the corpus. So this gives us an algorithm. We begin by initializing our counts to 0, form a normalizer, then we can compute up the expected counts, and also compute the total number of times that we saw any particular foreign word. We'll need both of these to compute our maximum likelihood estimate, and after we've computed expected counts over all of our sentences, we can form those maximum likelihood counts, and then this gives us our word translation probabilities again. We go back through with these new parameter estimates and recompute the counts, and we keep doing that until our probabilities stop changing. So here's an example of what happens on a very small corpus. If you have these sentences and you start with uniform translation probabilities, after one iteration they get fairly peaky, and then they get peakier and peakier until you finally get the right answer. The problem with these lexical translation models is that they often get tripped up by selectional preferences. And so, for example, klein can be translated as either small or little. But in some phrases, you prefer one over the other. So, for example, small step is far more popular than little step in English. And so how do we know which to prefer? We can use a language model, and we can combine the language model score with our translation probabilities. And this is just an application of Bayes' rule. We want to find the best English sentence that comes from a foreign sentence, and so what we need to do is we need to compute the maximum English sentence that maximizes the combination of the English sentence and the probability of an English sentence we assume comes from a language model, and then we use our translation score to compute the probability of the English sentence being the translation of the foreign sentence. And the way that this was originally presented is as a noisy channel model. So you pretend that every sentence originally began as an English sentence that came from some language model, and then it was put through a noisy channel, translated into another language, and then you receive this garbled foreign string. And so what you need to do is decode the foreign string into what the original English sentence was. So this is why you combine the language model with the translation model. Okay, so that's IBM Model 1, but what has come after that? Models 2 through 5 become much more complex. We won't go into the details, the book talks about them a little bit, but IBM Model 1 is the only one that has a global maximum. It's the only problem that's convex. And for higher order models, you need to do more complicated machine learning techniques. IBM models have a historical importance that's hard to overstate. And it introduced important concepts like statistical models of translations, generative models, EM training, reordering methods. They're not used much anymore, but they still form the foundation of all of the statistical translation models that came after. And they're still in common use for the task of word alignment, which is an important pre-processing step for just about every machine translation algorithm that is used popularly today. So why aren't these word models used as much anymore? So here are some examples. So take a look at this sentence. Michael geht davon aus, dass im Haus bleibt. And so what happens in this sentence is that you have the German phrase geht davon aus being translated into one English word. And so if you have a word-based model, you're going to lose some of that intuition that assumes is associated with all three of these German words when they appear in one contiguous span. And the IBM models really depend on this word alignment. And in some cases, it's very hard to align English words with German words. So for example, John wohnt hier nicht, it's hard to align does with any of those words. This becomes an even bigger problem when you're dealing with things like idioms. So, John biss im Glas, that literally means John bit the grass. But figuratively, it means that John died. And then you have this English idiom on the other side, John kicked the bucket. And if you literally align these words, you'd have that glass is being aligned with bucket. And obviously, that isn't a good translation. These things only make sense when you consider these as whole phrases in translating the entire idiom. And so this is what later models do. And if you want to find out more about this, please take the next sequence of computational linguistics, where you'll talk about some of these phrase-based models for machine translation. Okay, so to wrap up, we talked about lexical translation, in particular IBM Model 1, and how you can use the expectation maximization algorithm to find alignments that best explain parallel text. So in class, we'll work through some examples to get you ready for the homework, which will be to create an IBM Model 1 translation algorithm.